Hello and welcome to today's exciting installment of physics. We'll be looking at Newton's second law. Newton's first law we already went over, talking about inertia and the resistance to change. Newton's second law dealing with when that change does occur. The first part of Newton's second law says that the acceleration of an object will be directly proportional to the net force acting on the object. So how much a object is going to accelerate will be related to the force pushing on it. That makes sense. If you push more, there's a bigger force, it's going to accelerate more. Nothing too surprising there. The second factor that will influence things is that it's inversely proportional to the mass of an object. Again, nothing too surprising there since they're inversely proportional. That means if our mass increases, then our acceleration will decrease. If you've got a larger object, more massive object, it's not going to accelerate as much. Think about pushing a bicycle or a car with the same amount of force. That bicycle is going to have a little bit more acceleration, it's going to move more. The car barely move at all because it's got that big mass. The way we could write that mathematically, our acceleration would be equal to the force, that net force, divided by mass. The way that we'll basically always be seeing it and looking at it is that our net force is equal to mass times acceleration. So that'll be one of our big ideas in today's lesson. That usually when we say what is Newton's second law, or if I refer to Newton's second law, I'm talking about that equation right there. The net force equals mass times acceleration, more so than the written out in English description. Some key ideas, really important ideas when we're dealing with Newton's second law. There's two fundamental conditions that can arise, and both of them have some pretty important implications. The first thing is that if something is moving at a constant velocity, that constant velocity tells us that the acceleration is 0 meters per second because the velocity is not changing, it's not accelerating, not speeding up, not slowing down. A second nice fact that comes out is that the net force then is 0 newtons. Looking back at Newton's second law, if it's mass times acceleration, mass times 0, then the net force is 0. So both of those things are 0. And a third thing, just when you're looking at like your free body diagram and looking at all the different forces, all of your forces must balance out. So if you know it's going at a constant velocity, you know all of those really useful things, and you'll probably be using some or all of them. They're all basically related, saying the same thing. The other fundamental case, if it's not moving at a constant velocity, I mean, it's accelerating, it's speeding up, it's slowing down. Maybe you're trying to find an acceleration, maybe you're given an acceleration. That tells you right there that it's not going at a constant velocity. So our acceleration is not 0 meters per second squared. That's sort of obvious. Our net force is not 0 newtons. So when you're looking at that free body diagram, all those forces are not going to balance out. Some of them, I mean, a couple will cancel out, but in the other dimension, essentially, those other two might not balance out. And that's where you'll be using then that summation of forces. When you put them together, it's going to equal mass times acceleration. You'll probably be using that somewhere in that question then. Look at just a really easy example to start with, and then we'll look at a more interesting and fun one. So in I should say, if A, 485 Newton of net force are acting on a 45.0 kilogram student, what is the acceleration of said student? So I guess I should be if instead of Ia, whatever Ia means. So we have 485 newtons of net force. They're acting on a 45 kilogram student. What's the acceleration of said student? So we're just looking at Newton's second law. The net force equals mass times acceleration. We've got the net force. We've got the mass. We just plug those two in, and it's pretty easy, pretty straightforward. So I'd plug in 485 newtons, plug in 45 kilograms. We're going to divide both sides by 45 kilograms, and that will give us then, with our 3 sig figs and our units, 10.8 meters per second squared. Pretty easy. Nothing too hard there. Another idea we want to look at, friction. We talked a little bit before about friction. It resists change. It goes against motion. We'll look now more at how can we calculate it and what are some more specific properties about it. There's two types of friction. One is kinetic. Kinetic means moving. The other type, if we're talking about something that's not moving, that's not changing, that would be static. Static means not moving in general terms, not just physics terms. And kinetic always deals with motion, movement, some sort of thing like that. So we got kinetic friction when something is moving, and static friction when something's not moving. And if you ever think about like just trying to, you got some big heavy object, you're trying to push it. When you're first trying to get it to start sliding, You might have noticed at some point, depending on how many things you push around and how often that comes up, honestly. But if you are trying to push a large object, just to get it started, you need to push really hard. And then after it started moving, once it's sliding, it still might be difficult, but it's not as difficult as it was to get started. That's because there's that static friction for overcoming just being in place in the first place. It's a little bit different. It's a little bit stronger. And then once it's moving, you have kinetic friction involved, friction of something moving. In either case, that force of friction is going to equal this Greek letter mu. It sort of looks like a U with a tail in the front, times the normal force that we were talking about before, that perpendicular force to a surface. So that mu, that U with the tail in front, that's our coefficient of kinetic and static friction. It's a Greek letter. You would say call it mu. So sometimes you might call it like mu k or mu s, depending on if it's a coefficient of kinetic friction or the coefficient of static friction, or you could just call it by that whole name, coefficient of kinetic friction. Some really good things to just be aware of with that mu. It's a coefficient. It's always going to go between 0 and 1. It's going to depend on the two surfaces that are involved, not necessarily on the mass, but like whether you're talking about sandpaper versus a desktop or ice and ice skates, you'd have different coefficients for those. It doesn't have a unit. So if you get an answer you solve for that, it's not going to have a unit. It's not newtons, it's not meters or anything. It's just all its own. It's one of our few things throughout the year that doesn't have a unit when you get the answer. And another nice little tidbit, like I was saying before, that mu s, that coefficient for static friction, is always going to be greater than that mu k, that coefficient for kinetic friction, for any two surfaces. Anything when you start it going is going to be a little bit more difficult than when it is already moving. If we ever do want to find that static friction, you want to figure out what that is. The trick for that one, you want to find the force required to just get something moving in the first place. That force that is required to just start it moving, that would be approximately our static friction force. You'd be able to set those two equal. So if you're told like, oh, it takes 650 newtons to just start the piano moving, that means that static friction for our piano is 650 newtons. So that makes it a little bit easier when you recognize that idea. We'll look at an example here using our Newton's second law and our force of friction here. A little bit more fun and exciting example. I know you enjoy those. In this example, let's say we have a student. It has a mass of 45.0 kilograms. That'll be our general student mass, so we don't hurt anybody's feelings by saying some are more mass than others or anything like that. It's being pushed by a mysterious physics force of 782 newtons as a punishment for crimes against humanity, and is being caused to accelerate at 12.5 meters per second squared to the right. So our student has maybe been thinking evil thoughts about physics or something, which would constitute crimes against humanity. They're being punished. They're being pushed by this mysterious physics force, and they're accelerating. We got three things we want to find in this problem. Part A, what is the force of friction acting on our student? Part B, what is the coefficient of kinetic friction? And part C, we're going to figure out how far does she go in 15.0 seconds if she started at a rest. So we'll start there with part A. Anytime we're dealing with forces, especially if you're in doubt, you're not sure what to do, the best thing to do every time is always start with a free body diagram. Look at those forces. What forces are we dealing with? So there's my student. They're a box. Take a moment, maybe you should pause and see if you can come up with those forces and see if there's anything you notice that might be useful, and then check and see if we agree with things. Hopefully you've taken a moment to look things over on your own. It's always best if you're actively participating. You get more out of this whole experience. For our student here, as we usually have, there's gravity, that weight pulling down. We're always pretty much doing stuff on Earth unless otherwise stated, so you got gravity. In our example, they're being pushed to the right. They're not falling through the floor or shooting up into the sky, so there's a force of gravity and they're probably on a floor or something. The normal force would be counteracting gravity. That's most often the case unless something is indicating otherwise. Other forces that are acting on it. Well, there's this mysterious physics force that's pushing on it. So I'll call that force punishment. You can come up with some other name if you want. And then the last thing, the question is asking for a force of friction, so there's probably friction involved. So that would be going opposite of our punishment force. And I noticed maybe in my picture, not necessarily perfect, but my force of gravity and force of normal are about the same. My force punishment is a bigger arrow though than my force of friction, because it tells us in this problem that our student is accelerating, they're pushing this, that punishment force must be stronger. A couple things just looking at this picture that are really good to recognize. Frequently, it'll be the case that our normal force and force of gravity are the same, unless there's something strange going on, we're at an angle or a ramp or something. Probably 99% of the time that'll be the case. So just a good thing to recognize. Another thing to recognize